Uh, so today I was supposed to discuss about two things. One is hierarchical clustering, and number two, I will also be talking about homework 4. So let's begin with hierarchical clustering. We'll just try to understand the basics of hierarchical clustering on a higher level, and then we'll program it out. And later, I'll give you a quick overview of homework 4 and how to solve it, a brief idea of how to solve it. Now, coming to hierarchical clustering, so there are in hierarchical clustering there are primarily two ways of clustering things in this method. One is using agglomerative, and number two is using divisive. So in agglomerative methods, what we do is initially, let's say we have PQRST. Let's say these are the data points that we are trying to cluster. We will start from the baseline and assume that each of individual point itself is a cluster in itself, and then we agglomerate each one of them and then form clusters. So here, as you can clearly see, if we start from PQRS, we can assume every single one of as an individual data point. And moving up the tree, like so, this is P comma Q and S comma T, R comma S comma T, and all this. So moving from bottom to up is agglomerative clustering. And in the other way, what is in divisive method of clustering? So we assume that the whole data set itself is a single cluster, and from there we will just divide the whole data set into multiple clusters. So that's what happens in divisive method. So how does it work? How it works. So if I take a small example for agglomerative clustering, so we can assume, like, first we'll start with these points, the closest one. So we'll basically take like whichever data points are closest to one another, and we cluster them together, and then we repeat until there is only one cluster. So that is nothing but this agglomerative clustering is what we were talking about. Now, one question that we generally will have is like, what is like, how do we know which two data points to cluster together, right? So that's the distance metric that we have to decide upon. What is the like, is it the Euclidean distance, or is it Manhattan distance, or is it something else? So that kind of distance metric is something that we have to decide. And apart from that, the other thing that we also need to decide is what kind of a linkage that does these data points should have. So we'll discuss about them a little further. But before speaking about them, there is also another way of pictorially representing these hierarchical clustering groups. They're called dendrograms. In dendrograms, you can see here one representation of a dendrogram. So, for example, let's say we want to have 4 clusters in the data set. Now, if you're given n equals to 4 and we're doing agglomerative clustering on the data set that we have, let's say we are moving from bottom to up. Essentially, this is the place where we have 4 clusters, right? So, and if you move little above, like this range in between A and B will be the place where you have 4 clusters. Anything above, it will reduce. Like if at all the A is in here, let's say it's like there's a line here, then it will have only 3 clusters, right? So like in this dendrogram representation, you can see like from bottom, let's say these are the data points that are clustered together initially: 9, 23, 17, 6, 11. All of these are the data points that are clustered together. And while moving up, and this is what the distance metric that I was mentioning earlier, like for example, 9 and 23 are clustered together because of a distance metric of 0.15, and they are closely related to one another, and that's why these two data points are clustered. And you move above the curve in a similar fashion, and you aggregate all these clusters, smaller clusters, into a bigger ones. and you'll get to a point where there are only 4 clusters in the entire data set, and that's what we are trying to end up with, right? Now, as I said, I was also talking about the linkage criteria, like how do you link 2 clusters with one another, right? Take the 2 closest clusters and make them into one cluster. So that's what we said before, right? But how do you define, like what is the distance metric, or how do you define one cluster is closer to the other cluster, right? So there are multiple ways of doing this. The first thing is single linkage. So in single linkage, what we'll do is we'll have to we'll take, let's say this is the data points that we have in the entire data set, and this is cluster R and this is cluster S. And if we are trying to find out the distance between these, like what do you mean by single linkage? Let's say the closest points in cluster R and cluster S is this Xi and Xj. So like whichever the minimum distance is between the points is there, that is nothing but single linkage rule. So minimum of d of xri comma xsj is what single linkage means, like taking the minimum linkage as the linkage rule. Now that's for the single linkage method. Now, similarly, there are also other types of linkages. So there is something called complete linkage. In complete linkage, we try to take the maximum distance between the data points in the sets R and set S. And that's what a complete linkage means. And in average linkage, we take the average of distances between each and every data point in each of the clusters. Now, we spoke about linkage metrics. Now let's also talk about distance metric. So primarily, there are many different types of linkage metrics that we have, but in this case, we'll use 2 distance metrics that we can discuss about. One is Euclidean distance, one is Manhattan distance. So in a 2-dimensional coordinate space, if I wanted to describe what an Euclidean distance is, let's say we have x1, y1, and x2, y2. And the distance between the distance d, the Euclidean distance, can be given by this formula, x1 minus x2 whole square plus y1 minus y2 whole square, and square root of that whole thing. So that is nothing but the distance, shortest distance Euclidean distance metric. And if you talk about Manhattan distance is this, for example, 1 second. Yeah, for example, let's say you are starting at this particular point and you're trying to move up to this point. So the Manhattan distance is like this block distance that you have. So this green line actually represents your Euclidean distance, and the yellow or red, all these things kind of represent your Manhattan distance, and that is given by a minus c plus b minus t. So this is your Manhattan distance. So this is like a fundamental concept. So essentially in hierarchical clustering, it's a very simple concept. So there are 2 different methods. One is agglomerative and one is divisive. Agglomerative is from bottom to top, and divisive is from top to bottom. So, and in agglomerative, primarily there are 2 different metrics. One is the linkage metric, and the second one is the distance metric. And linkage metric, primarily we'll think about, there are also different other types of linkage like word linkage and all, but primarily single linkage, complete linkage, and average linkage are the ones that we'll need for this course. And coming to the distance metrics, there are 2, Euclidean and Manhattan. So this is like a brief overview of the concept. Before going into the code, I'll take a quick round of questions. Anyone have any questions? Okay, if not, I'll I will move forward. So so the coding strategy is pretty simple. We're taking in this particular while trying to understand this concept, we'll take something called mall customers CSV. Essentially, it's kind of a data set with annual income and spending score, and we'll try to club these customers based upon their spending score. That's what we are trying to do now. So I'll just quickly run through the code. First, let's like importing different kinds of modules. That's the first block. That's what it's doing. And coming to the second block, we're reading all the data into pandas data frame, and in that data frame we're getting the values of a specific column, and so here if we so we're trying to like first I wanted to show you about the dendrogram, like how to figure out the total number of clusters for spending income and spending score. And if we plot these data points in an x y coordinate system, this is how they're going to look like. So so you can think of it like, if at all their spending score is, for example, if at all their annual income is somewhere around 23K, so their spending score is about 100. So this is how the whole cluster is there. And if I wanted to kind of build an agglomerative clustering model on this, for just this 20 points that I've taken here, for the top 20 points in the data set. So here you can see that on the x-axis we have the customers listed, and in the customers we have like so 7 and 11 and 19. So 11 and 19 are like kind of have a similar pending score, and that kind of can be seen here. For example, let's say 11 is something this and 19 is something this. Maybe somewhere around here it is there. So they both are combined together as one. And let's say if I wanted to cluster all the customers into 3 or 4 clusters, I'll basically cap the customers at this particular. Let's say if I draw a line at this, that essentially means I'll have 4 customer groups, right? Now that's using dendrogram method, but most of the times we'll just use hierarchical clustering using a standard method called hierarchical clustering in agglomerative clustering in our scikit-learn package. So how do we do that? So first of all, I'm creating an object called agglomerative clustering, and I'm defining the total number of total number of clusters that I should given. So I'm telling the total number of clusters are 5, and the affinity is Euclidean. Affinity is nothing but the distance metric that we were talking about earlier, and linkage metric is single, and now we are trying to fit this whole cluster to the data that we have. Now, as you can see, it's pretty straightforward and pretty simple to implement, but it generally gives out a good insights on how the data is distributed, right? And if I want to visualize this clusters, so this is how I can visualize this clusters, right? So here you can see the whole data points, like for annual income between 15 to 23K, and if the spending score is between 0 to 100, and how do I cluster them together? So this is how the clusters are formed. So here you can see each cluster is given a separate color, and all the blue represent they belong to the same cluster, and all others present they belong to the similar cluster. And it kind of makes sense here because you can see they all have like a similar kind of spending potential towards the end, right? So that concludes the first part of the discussion. So any questions on this, or should we just skip to homework 4? Okay, so let's quickly look at homework 4 and what we are trying to do there. And if time permits, I'll leave last 10-15 minutes for questions. Okay, so so one question that I have was, we're also working on PCA, but did the professor in the class explain about PCA or not? principal component analysis?
I don't think so.
Okay. Okay, then I'll quickly give you an introduction to principal component analysis. Then, so that it makes sense, then I'll explain about PCA. I won't.
Hello, Stai. I have a question for the have a quick question for the homework 4.
What?
I have a quick question for the homework 4.
Yeah.
So for the homework 4, 1.1 and 2.2, they are only typing is okay, the no coding, because it told us to explain something. Looks like so 1.1 and 2.2, they are both just the typing is okay, but not coding.
Yes. Yes.
Okay.
I think they're both. We'll discuss about the questions that were asked, but primarily they were, they were theoretical questions. We were just trying to test out how well do you know the concepts. So that's what it is. Now I'll just give a quick introduction to PCA. Let me. Okay, I can. There's this interesting. I was just looking at some PCA on towards data science. There's this guy who was put in a really good way. So what in a simple manner in PCA, what we're trying to do is we're trying to reduce the dimensionality to a lower thing. For example, let's say you're trying to predict a cat face, or you're trying to predict the stock market based upon multiple different parameters that you have. Now the price, let's say the predictor variable that you're trying to predict is nothing but your price of a particular share. Now this particular share might be dependent upon some 1,000 different variables, right? It can depend upon the particular season, the particular day, how the market sentiment is. Are there any external factors like the Ukraine war is happening? And there are things like there are uncontrollable parameters also are there. There are something like, what do you say? What else can affect a stock price? Yeah, there are like some thousands and if not tens of thousands of parameters that can affect a particular stock price. Now let's say you're trying to predict this, and if at all you wanted to train your model and try to predict everything from this particular aspect, right? The one straight away problem that you're going to face is like, because there are a lot of features in the data, it will be difficult for you to train. And obviously, when you look at the historical data of this particular stock and how the people are investing, it is possible that you have a humongous amount of data, and if at all you have these many parameters, it will be difficult to train, right? So how do we solve this problem, right? So how do I reduce this dimensionality to a lower dimension so that you can train the model with lesser amount of resources? So that's what that's where PCA, things like dimensionality reduction, comes into picture. There are two different types of methods in dimensionality reduction. One is linear methods and non-linear methods. And for the scope of this course, we are just, I think we'll talk about PCA. And that is nothing but one of the linear methods which can solve this dimensionality problem. So essentially what we are trying to do is, for example, let's say there are 1,000 features in this data set. I mean, 1,000 columns in this data set. We'll try and reduce this 1,000 columns into 2 columns, ensuring that the variability is still the same in the data points, right? So that's what, how will we reduce this from 1,000 to, let's say, 2 features, 1,000 to, let's say, 3 features. How it's done, I think that's something is what Professor will explain in the next course, in the next class. But essentially, what for the scope of this discussion, what you need to understand is you have some, let's say, 1,000 features. We are trying to reduce this to lesser number of features, and ensuring that the dimensionality is still intact. Now, an example of this, I think we can quickly look through in here. Like there are so there is this CT head data set of there is this breast cancer data set. There are some 30 columns in this. Essentially, in the blog, what he will do toward the end is he will reduce the total number of data points from 30 to 2. Like this is PCA2, where you have only 2 principal components, and this is malign and benign, malignant and benign. So this is how they look like. PC1 is the principal component 1, and PC2 is the principal component 2. And you forecast all the data points onto this 2-dimensional plane, right? So that is with number of components is equals to 2. And if at all you're going with a higher number of components, let's say we have 3 principal components in a 3-dimensional space, this is how we can visualize those data points. As you go into the higher dimensions, you can have it at 4, 5, 6, anything, pretty much any number of components that you want, but you won't be able to visualize it like this, right? So I hope the one thing that I want you guys to take away from this is basically we have a data set with higher number of dimensions, and we are trying to reduce this total number of dimensions from 1,000 or 10,000 to a lesser number of dimensions, let's say 100 or 50. So that's what we are trying to do. And the way we are doing it using the PCA, principal component analysis, which is a linear method, which ensures the variability of the data set is actually captured, right? So that's pretty much what we are doing. Now let's see a simple application of this that's what we've asked, like a very simple thing in homework 4, right? So in homework 4, if I wanted to explain, so here I think we have given you around 1200 bit strings, each of them containing 16 bits. And to explain you what's happening and how we are trying to cluster data points together. So here, let's say we have an example. Here they have given an example. Let's say we have only 4 bit strings. Each of the bit strings are 0, 0, 0 and 0, 0, 1, 0 and 0, 1, 1 and 1, 1, 0, right? So now how do I cluster all of these together? It's based on distance metric. So we have to decide what kind of a distance metric that we should use. Like, should we use a Euclidean distance metric, or should it be a Manhattan distance metric? And if it is so, and what should be the threshold value, what you should put for the clusters to be together, right? Now, essentially, if you think about each of this bit as a single dimension in an axis, and if you try to figure out the Euclidean distance between the data points, then you will kind of understand where and how to get this threshold, and how to get this threshold and how to decide which distance metric will be very appropriate for this, right? So like, how are we clustering? Once again, coming to that question. So for example, let's say we're able to achieve this, we are saying that 0, 0, 0 and 0, 1, 1, 0 are belong to the same cluster, because there are some transformations on top of this bit string. These are 1-bit transformations, by the way. Like, you're just allowed to flip only 1 bit at a time. So if you flip this 1 bit, so this will go to this, and if you flip 1 more bit, this will go to this. So this is the 1-bit transformation that you're doing. And since this 1-bit transformations actually result in this, all these 3 will be aggregated into a single thing, and it's called one cluster. So that's what we are trying to achieve using this problem. So now, as I said, there are 2 different parameters that you need to pick. First one is linkage metric, as I explained earlier. Like, should it be a single linkage, complete linkage, or average linkage, and why you're picking that linkage? You should explain it properly. And what is the distance function you will use for it? Like, is it an Euclidean Manhattan or something like cosine distance? And what should be the threshold distance be? So as I said, if you think about it like not as a complete bit string, but as an individual individual axis in itself, then you can figure out, like, it's pretty easy to visualize like what kind of distance metric that you should use for this problem. And once I think so I think the most difficult part for you is to figure out first three questions. I think from there on it'll be very easy for you to move forward. Then we are asking you to do the agglomerator clustering, and we have seen how to do agglomerator clustering. And then we're also asking you to do k-means clustering so that you can actually see how k-means and hierarchical clustering differ from one another. And finally, we are also asking you to do the principal component analysis. And in PCA, essentially what we are trying to do is, we are, as I said previously, we are trying to have PCA is kind of a dimensionality reduction technique where we are trying to reduce the dimensions from higher dimensions, like some 16 or something. I think for this problem, we're trying to reduce the dimension from 16 to 2, and we're trying to visualize how these components are varying, right? So yeah, so that's pretty much about homework 4. It's kind of a little bit different from all other homeworks that you have done. You have little more of theoretical side to it because you need to understand how to choose each of these parameters. And once you have figured it out, I think it's pretty straightforward to solve this problem. So yeah, I think that's it for today. If you have any questions, I'll take them, or we can end this discussion. Any questions?
When are the like the previous Jupyter notebook we were just looking at with like the agglomerative clustering, or
Yeah.
like when are we gonna get a link to that notebook in particular?
It's already there, right, on the canvas. Were you not able to see that?
I mean, yeah, it's just like usually I have to ask because like when I click on them like during the discussion, I can't really access anything in there.
Oh, does it say you have an access problem?
Or I mean, it's like, or like previous times whenever I tried accessing discussion materials.
Okay. I think some of these materials were linked to the previous time. I think that's why you're having this problem. I think I will recheck it and I'll re-upload all of the material. Okay.
All right. Yeah. Thank you.
Welcome. Okay, I'm gonna stop the recording now, and let's see if there are some questions. What about the Hamming distance? Sorry, didn't see that we only have yeah, there are different types of distance metrics that we have. You can pretty much use and if you think about it, this is also a hyperparameter, right? Like which kind of thing uses for better for what, or something that you need to decide, and that depends upon what your end objective is. So yeah, it can be anything, is what I'm trying to say. Okay, I'm gonna stop the recording now.